Hello everyone. I am Siddhartha Pramanik and I am a research scholar from the Department of Mathematics, IIT Kharagpur. This is the final live interaction season for this course, Introduction to Abstract Group Theory. I am supposed to solve some problems related to the content of week 8. So, before that, I will briefly summarize the content of week 8. Then I will start solving some problems. Okay, in this week we have basically learned about the Silos theorem and their applications. So, first of all, we have learned about Silo P subgroups, and then we have saw three Silo theorems, and then we have heard about one particular type of group named as product group. So I will come to it because it was not uh, described in so much details in the lectures. And probably one more special type of group known as P group. So I will come to this thing also later. Let me quickly write down this three silos theorem, not in detail but in short, because I will be using these theorems in the problems repeatedly. So in all three silos theorems, G is a group and order of G is P power E times M, where P is a prime number and P does not divides M. So the first theorem is about existence of Silo P subgroup. So first theorem is G has a Silo P subgroup. And second Silo's theorem is that all Silo P subgroups are conjugate. All Silo P subgroups of G are conjugate. And the third theorem is about the number of Silo P subgroups. So the number, let's say SP of Silo P subgroups. Okay, so let me write if if SP is the number of Silo P subgroups, then SP must divide M, and second one is SP is equals to 1 plus P times A, where A is some natural number. So this is the brief of three Silo's theorems. So I will basically start with some applications of Silo's theorem. Then I will go to the some information about P groups, which also includes class equations of some P groups. Okay, so let's start with the first problem. So the first problem is how many silo 5 subgroups of the permutation group S5 are there. So we need to basically count the total number of silo 5 subgroups of S5. So the first, to solve this question, we first need to know what is the order of a silo 5 subgroup in S5. So what is the cardinality of S5? It is just 5 factorial, right? So it can be written as 5 times m, where 5 does not divides m. So order of the silo 5 subgroup is 5. So order of a silo 5 subgroup in S5 is 5. So that means we need to count the total number of subgroups of order 5 in S5. So let s small s of subscript 5 is the number of silo 5 subgroup of S5. Now we can, by using Silo's third theorem, we can get some possibilities, right? We may not get the exact number, but here we have another tool. So basically, uh, a group of order 5, let's say H, it is always isomorphic to Z mod 5Z, right? Because a group of order 5 is always cyclic because it is a group of prime order. So it has to be isomorphic with Z mod 5Z. Now in Z mod 5Z, uh, so okay, let me write it here. So this is the number of subgroups of order 5 of S5. So a subgroup of order 5 is cyclic. So it is generated by a single element. Means it is generated by an element of order 5. So if we can found the total number of element of order 5, then we are done, right? Because it is actually number of elements of order 5 in S5 divided by, so we will found the total number of element of order 5 in S5, and we know in a group of order 5, okay, let me write, because in a group of order 5 there are exactly 4 elements of order 5. So we can find the total number of elements of order 5, and if we divide it by 4, then we will get the total number of subgroups of order 5. So we just need to find this number. And how to find the total number of elements of order 5 in S5, we have already saw that in previous seasons. So an element of order 5 in S5 is basically a time cycle, right? So we need to basically found the total number of 5 cycles in S5. So that is actually equals to number of 5 cycles in S5 divided by 4. And number of 5 cycles, we know it is looks like A, B, C, D, E. So A has 5 choice, B has 4 choice. Similarly, C has 3, D has 2, and E has 1. And a 5 cycle can be written in 5 ways, so we will divide it by 5. So this is the number of 5 cycles. So this is basically 5 factorial by 5, and we are dividing again it by 4. So this is 3 factorial. So this is the final answer. Is it okay? Okay, I hope this is okay. So similarly, if I ask, so what is the number of silo 7 subgroups of S7? So then can you count it in a similar way? Just try.
120.
So it will be basically 5 factorial. So this is just total number of 7 cycles, which is 7 factorial by 7, and you need to divide it by 6, because in a cyclic group of order 7 there are exactly 6 elements of order 7. So this is basically 5 factorial. So actually we can generalize it uh, in this way. So let P be a prime number, then the number of silo P subgroups of SP is equals to P minus 2 factorial. So you can try to prove it in a similar manner, because nothing exactly you have to change it. So basically I want to say that we don't have to use this Silo's third theorem here, because we can count the total number of subgroups manually. So I hope this is clear. Now before moving on another applications of Silo's theorem, I want to mention some things about product groups, because you need to know these things and I will be using this thing. So let me mention that. So product groups. So let me define it first in a proper manner. Then I will just mention some properties without proof, which I will use in the next problems. So let G and G prime be to any group, be to groups. Then we can define another group structure on this Cartesian product of these two sets. So we all know how to define Cartesian product of two sets. How to define a group structure on this? So we need to define a binary operation. So let us do that. So for G1, G1 prime and G2, G2 prime belongs to this Cartesian product. We define G1, G1 prime dot G2, G2 prime. So we are defining multiplication operation in this product set. So this is just G1, G2, comma G1 prime, G2 prime. So observe that here this is the operation in G and here it is the operation in G prime. Then with respect to this operation, with respect to the above, let's say binary operation, G cross G prime forms a group. And this group is named as product of G and G prime. Okay, you can define it for any group G and G prime. So this is the definition, and I want let me list some important properties of this. So the first property is uh, the product G G prime is abelian if and only if both G and G prime are abelian. Second one is if both G and G prime are finite groups, then we know how to count the cardinality of this Cartesian product. It is just product of cardinalities. Third, if both G and G prime are finite groups, then this Cartesian product is a cyclic group if and only if both G and G prime are cyclic and their orders are relatively prime. Means GCD of order G and order G prime are 1. And the fourth one is if G belongs to G and G prime belongs to G prime such that their orders are finite, then order of this element in the product group, it is also finite and it is equals to LCM of order G comma order G prime. So and also one last thing, if we take just product of Z mod N1Z with Z mod N2Z, then this will be isomorphic to Z mod N1 N2Z if and only if GCD of N1 comma N2 is 1. So these are the 5 properties I want to mention. Let me repeat again. So the product group is abelian if and only if both G and G prime is abelian. Second is, if both groups are finite order, then their Cartesian product is also finite order, and its order is just the product of the two groups. Third one is, if both the groups are of finite order, then their Cartesian product is cyclic if and only if both G and G prime are cyclic and their orders are relatively prime. And the fourth one is about the computing of order of an element in the product group. And the third one is basically a result which says if we product two cyclic groups, so when their product group is cyclic. So Z mod N1Z is a cyclic group, Z mod N2Z is also cyclic. So their Cartesian product is cyclic if and only if N1 and N2 are relatively prime. Okay, I hope just remember these properties. You can found the proof of these properties in any standard book. So if you are interested, you can look. Now let's move ahead and see some more applications of Silo's theorems. So that every group of order 175 is abelian. Okay, so we need to show if we take a group of order 175, then it has to be an abelian group. So let G be a group of order 175. So we want to use the Silo's theorem, right? So let's find the prime factorization of 175. So 175 is basically 5 square times 7, right? So 5 is a prime factor as well as 7 is a prime factor. So by first Silo's theorem, it has Silo P subgroup as well as Silo 7 subgroup. Okay, so let S5 equals to the number of Silo 5 subgroup of G, and S7 the number of Silo 7 subgroups of G. Now a Silo 7 subgroup has order 7 and a Silo 5 subgroup has order 25. Okay, so just observe that. Now we need to find the exact numbers. So let's try to find it. Now by Silo third theorem, so S5 will divide 7 and S5 is equals to 1 plus 5a, right? So from this, can you say what is S5?
1.
Yeah. So S5 has to be 1 because it can be 1 or 6 or 11 or so on, but it has to divide 7 also. So we have only one possibility, which is 1. So similarly, let's find S7. So S7 must divide 25, and S7 is equals to 1 plus 7a, where a belongs to n. So it can be 1, it can be 8, it can be 15, it can be 22, and so on. But it has to divide 25 also. So the only possibilities is S7 is equals to 1. So that means we have only one Silo 5 subgroup and only one Silo 7 subgroup. So G has exactly one Silo 5 subgroup, let's say H, and exactly one Silo 7 subgroup, let's say K. So because these are unique, H and K, so they are normal subgroups. Also, H comma K are normal subgroups. Okay, so now the fact is we can define the product group H cross K, and from that we can define a homomorphism to G by just H comma K map it to HK. Then you can show that this will be an isomorphism because same thing has been done in the lectures also. So you can just repeat the process. So phi is an isomorphism. So you just uh, do it by yourself or just review the lectures. So that means G is isomorphic to H cross K. Okay. So now you see that K is Silo 7 subgroup and its order is 7. So K is isomorphic to Z mod 7Z. But what about H? H is a Silo 5 subgroup of order 25, means 5 square. So H is a group of order 5 square. So what can you say about H? So basically, in the lectures we have saw uh, every group of order p square is abelian. So you can check the lectures that it has been proved in the lectures also. So the fact is both H and K are abelian. So their Cartesian product is also abelian. And because of this isomorphism, G has to be abelian. Is it okay? So I hope it is okay. So we have proved that every group of order 75 is abelian. So observe that this is a group of order p squared times q, where p and q are distinct primes. So one remark is using the same method, one can prove that every group of order 45 is abelian. So you can try it on your own by arguing in the same way. So this is problem number 3. Okay, let's see a different kind of problem. So that a group of order 56 has a proper non-trivial normal subgroup. So that means a group of order 56 cannot be simple. So if G is a group of order 56, we need to produce a proper non-trivial normal subgroup. So let G be a group of order 56. So proper means proper subset and non-trivial means non-identity. I hope you are well aware about the terminologies. So as we are using the Silos theorem, so we need to find the prime factorization again. So order of G is 56, which is equals to 2q times 7. So it has Silo 2 subgroup and also Silo 7 subgroup. And Silo 2 subgroup has order 8, Silo 7 subgroup has order 7. So let's try to find the number of Silo 2 subgroups and number of Silo 7 subgroups. So let S2 is the number of Silo 2 subgroups and S7 be the number of Silo 7 subgroups. So let's apply the Silo's third theorem to find possibilities of S2 and S7. So then S2 must divide 7 and S2 is of the form 1 plus 2a. That means it can be 1, it can be 3, it can be 5, it can be 7, it can be 9 and so on. But since it has to divide 7, we have only two choice. So S2 is either 1 or it is 7. So similarly, S7 has to divide 8. So it has to divide 8 and S7 has the form 1 plus 7a. So that means it can be 1, it can be 8, it can be 15 and so on. But from this condition, we have S7 is either 1 or 8. So from Silo's third theorem, we can say only up to this. S2 has these two possibilities and S7 has these two possibilities. So now, if at least one of S2 or S7 is 1, then that corresponding Silo subgroup is unique. So that will give you a non-trivial proper subgroup. So then we are done. Okay. So assume S2 is also 7 and S7 is 8. Means this case is not happening. We are assuming that. So then what happens? So then G has 7 silo 2 subgroups uh, of order 2q means 8. So let's put name for them. Let's say H1, H2 up to H7. Also G has 8 silo 7 subgroups of order 7. Let's put a name for these things also. Say K1 up to K8. Okay. Now, a group of order 7 is always cyclic because it is of prime order. Let's use this fact. So, since a group of order 7 has 6 elements of order 7, because 7 is of prime order. So every non-identity element has order 7. Okay, I will use this fact later. Okay. So this K1, K2, K8 all are groups of order 7. So what can you say about the intersection? So what is the order of their intersection? Can you say? So let's say K1 and K2. So what is this order? So can you use the Lagrange theorem? So Ki intersection Kj, it is, okay, let me write. Now Ki intersection Kj is a subgroup of Ki as well as it is a subgroup of Kj. So by Lagrange's theorem, its order must divide order of Ki, which is 7. But 7 is a prime number. So Ki intersection Kj has to be 1 or 7. But can it be 7? So it cannot be 7, right? So this implies Ki intersection Kj has order 1, because if Ki intersection Kj has order 7, then Ki intersection Kj is equal to Ki and it is equal to Kj. But I and J are distinct. So Ki and Kj are distinct subgroups. So they cannot be equal. So it is for all I not equals to J. So what is this cardinality? I equals to 1 to 8. So their intersections are always trivial. So let me, so suppose this is your K1, this is your K2, this is your K3, and so on. But here intersection, you have only one element. So K1 union K2, how many elements are there? Just 50. So this union has at least, uh, let's say 8 into 6 means 48 elements, because each Ki has 6 elements of order 7, and those 6 elements are unique. So you must have at least 48 elements. Okay, I hope you have understood. So this implies, okay, let me write it here. Now let's come back to CO2 subgroups. So uh, so again, okay, let HI. So what is the possible order of HI intersection HJ? It must divide 2Q. So it can be 1, 2, or 4, because it cannot be 8, right? Because CO2 subgroups are distinct for I not equals to J. So this implies, uh, what is union of H1 and H2? It should contain at least, let's say, 12 elements. Because let's say this is your H1, this is H2, and this is their intersection. This has 8 elements, this has 8 elements. This intersection is less equals to 4 elements. So the total uh, has to be at least 12 elements. So this implies cardinality of G is at least 48 plus 12, which is 60. But this is not possible, right? Because we have started with a group of order 56. So what went wrong? So we have assumed that H2 is 7 and S7 is 8. So this is cannot be possible. This is wrong. Hence, either S2 is 7, or sorry, S2 is 1, or S7 is 1. So at least one of the silo subgroups has to be unique. So one of them has to be a normal. Hence, either G has a unique SILO2 subgroup or a unique SILO7 subgroup. So one of them has to be unique. That means one of them has to be normal. So this completes the proof of this problem. Is it okay, or if you have any doubt, you can ask. Okay, I hope you have understood this. So let's move on to a next problem. So this is problem number 5. So in the lectures, you have saw that every group of order 15 is cyclic. So I hope you have saw this. So I want to say that something more general is true, and I want to do it now. So let P and Q be two distinct prime numbers with P less than Q and P does not divide Q minus 1. Then every group of order PQ is cyclic. So in case of group of order 15, it is 3 times 5, right? And 3 does not divide 5 minus 1, 4. So this is a particular case, this problem. So this is a very standard problem in Silo's theorem. So let's do the proof of this. So let G be a group of order PQ. So P and Q are prime numbers. So G has Silo P subgroup as well as Silo Q subgroup. So let's try to find the number of them. So Silo P subgroups is denoted by small sp, and it divide Q, and it has to be of this form 1 plus PA, right? So that means it can be yes. So it can be 1 plus P, 1 plus 2P, and so on. So what can you say about sp from here? So first of all, sp divides q, and q is a prime number. So that means sp is either 1 or it can be q, right? So can sp equals to q? So if sp is equals to q, that means 1 plus pa equals to q. So that means pa is equals to q minus 1. So that means p divides q minus 1. But this is not possible, right? Because we have assumed p does not divide q minus 1. So this is a contradiction. So sp is equals to 1. Okay, I hope this is clear. So G has unique silo P subgroup. Now what about SQ? So SQ divides P, that implies SQ is equals to 1 or P, and SQ is of the form 1 plus QA. So it is equals to 1 plus Q, 1 plus 2Q, and so on. But P is less than Q, right? So SP not equals to P. So this implies SP is equals to 1. So G has unique silo P subgroup of order P, let's say H, and has a unique silo Q subgroup of order Q, let's say K. Since they are unique, so they are normal. So as earlier, just define phi from H cross K to G by sending H comma K to HK, and so that phi is an isomorphism. So then it will follow that H cross K is isomorphic to G. But what is H cross K? Now H cross K is isomorphic. So H has order P. So it is isomorphic to Z mod PZ. And K is of order Q. So it is isomorphic to Z mod QZ. Now just use the last property of product groups. Yeah, this one. So Z mod N1Z cross Z mod N2Z isomorphic to Z mod N1 N2Z. And when this happens, when N1 and N2 are relatively prime. Since P and Q are distinct primes, so they are relatively prime. So this is isomorphic to Z mod PQZ, and this is a cyclic group. So G is a cyclic group of order PQ. Hence G is cyclic. Is it okay?
Okay, sir.
Yeah, okay. I hope others also have understood. So, yeah, okay. So we have generalized that every group of order PQ where P is less than Q and P does not divide Q minus 1 is cyclic. Let's do a small application of this. So that a group G of order 60 cannot have center of order 4. So that means order of ZG cannot be 4. So we need to prove this. So I hope you have understood the problem. So to do this problem, uh, we need to use one theorem which is known as G mod Z theorem. Okay. So what it says? It says if G mod ZG is a cyclic group, then G is abelian. So I hope you can recall this theorem. It was done in the lectures. So now if order of ZG is 4, then what is the order of the quotient? So order of then G mod ZG is equals to 15, right? But every group of order 15 is cyclic. So then G mod ZG is a cyclic group. So this implies G is an abelian group by G mod Z theorem. And hence G equals to ZG. And this will imply order of G mod ZG is 1. So this is a contradiction. So order of ZG cannot be equals to 4. So I hope this is clear for you. So G mod ZG is a powerful theorem. One should remember this. So a group of order 60 cannot have center of order 4. This is for any group of order 60. Okay, now let's do a theoretical problem which I will use in the next problems. So in the Silo's third theorem, so this says about the number of Silo P subgroups, right? And all Silo P subgroups are conjugate. Now we will see a exact formula for this. So this is problem number 7. So let G be a finite group and H be a subgroup of G. Then the number of distinct conjugate subgroups of H is equals to the index of NH in G. So NH is the normalizer of H. I hope you are aware of this. So it is basically this index. The number of conjugate subgroups of H is equal to index of NH in G. So let's prove this. Then I will come to the useful facts about this theorem. So proof is easy actually. So I hope you have understood the statement. So we need G has to be finite group. Okay. So G is a finite group. H is a subgroup. Then the number of distinct conjugate subgroups of H is same as this index. Okay. So let's see the proof. So consider this set S, which is the set of all conjugate subgroups of H. So means it looks like GH G inverse, where G varies over all G. So it is collection of all conjugate subgroups of H. So cardinality of S is the number of conjugate subgroups of H. So we need to prove cardinality of S is same as this index, right? So how to prove two sets has same cardinality? So we need to basically define a bijection between those two sets. Okay, so let's do it. So define F from this set of all cosets to S. And how we will define? So F of this coset is same as GH G inverse. So this is set of all left cosets of NH, right? This may not be a group, but this is a set. So every element is a left coset, like this. So we are defining this function f as G times NH mapped to GH G inverse. Since this is a conjugate, this lies in S. So this function is well defined. So we will prove this is a bijection. So how to prove f is 1 1? So if f of g and h equals to f of g prime and h, then we need to show g and h equals to g prime and h to show it is 1 1. So it is by definition. So this implies gh g inverse is equals to g prime h g prime inverse by definition of f. And from this we can write g prime inverse g h g inverse g prime is equals to h. So we are just multiplying with G prime inverse in both side and from left, and G prime from the right. So this will imply that this element belongs to the normalizer. G prime inverse G belongs to normalizer of H, because it is by definition, right? So how the normalizer looks like? It is A belongs to G such that AH, A inverse is equals to H. And from this we can say G prime NH is equals to GNH. So this is by the property of left cosets. So we have started with f of GNH equals to f of G prime NH, and we have proved G prime NH equals to GNH. So f is 1, 1. So now we need to prove f is on 2. So this is easy actually. So let GH inverse be a conjugate subgroup of H. We need to find a pre-image for this. So then GNH, this left coset, belongs to this set G mod NH. And what is the image of this? This is basically GH inverse. So F is on to clearly. So that means F is a bijection. Hence, F is a bijection. So, cardinality of S is same as cardinality of this set of left cosets. And this is same as index of NH in G. So this completes the proof. So I hope you have understood the proof. So basically we have found the number of conjugate subgroups of H. So the useful fact is, so if G is a finite group and H is a CeLO P subgroup, then the number of CeLO P subgroups of G is basically same as the number of uh, conjugate subgroups of G, conjugate subgroups of H, because all CeLO P subgroups are conjugate, right? That is by the second CeLO theorem. So that is the number of conjugate subgroups of H, and this is basically index of NH in G. So this gives you the exact number of CeLO P subgroups. So I hope you have understood.
Yes.
Yeah, okay. So let's see a problem related to this. Okay, let me write down it. So prove that every group of order 375 has a subgroup of order 15. So you take an arbitrary group of order 375, then always it has a subgroup of order 15. So you need to prove it. Okay, so let's start with an group of order 375. So let G be a group of order 375. So we need to produce a subgroup of order 15. So what is the prime factorization of 375? So it is basically 5q.
5 cube into 3.
Yes. So it is 5q into 3. So it has silo p subgroup of order 5q, which is 125, and silo 3 subgroup of order 3. So let's try to find out the numbers. Okay, before that, uh, okay, let's find out. So then the number of silo 5 subgroups, which is S5, it must divide 3, and S5 is of the form 1 plus 5a. That means 1, 6, 11, and so on. So that means its S5 has to be 1. So it has a unique silo 5 subgroup. And for S3, it has to be divide 5q, and SQ is of the form 1 plus 3a, which is 1, 4, 7, 10, and so on. So from this, you can check that S3 is either 1 or 25. So this, you just check it by these two condition. First one of this, second one is this. So we have two cases. One is S3 is 1 and the other is S3 is 25. So case 1, S3 is 1. So then G has a unique silo 3 subgroup. And remember that S5 is 1, that means G has always unique silo 5 subgroup. So let's say this one is H. So unique means it has to be normal, and let's say the silo 5 subgroup is K. Now both H and K are normal. Okay. Now order of K is 125. It is 5q, right? So 5 is a prime number. So it has an element of order 5, or let's say it has a subgroup of order 5. then K has a subgroup of order 5, say K prime. Okay, so then H K prime is a subgroup of G. Now why it is a subgroup of G? Because H is normal and K prime is subgroup, so their product is a subgroup. If you remember this, I have done this problem in earlier seasons. So product is a subgroup when one of the subgroup is normal. So H K prime is a subgroup of G. Now, and what is the order of H K prime? So it is exactly equals to 15. Why it is 15? Because you can define this function in the same way. And you can check it. Phi is an isomorphism. So we are just repeating the same method. That's why I am not doing it. You can go back to the lectures and check it. So phi is an isomorphism means order of H cross K prime is same as order of HK. And this is equals to 15. So in the first case, we have produced a subgroup of order 15. So I hope you have understood this. Let's do the second case. Now case 2. Case 2 means the number of SILO3 subgroups is 25. Okay. So this is our second case. Now number of SILO P subgroups is this index, right? So let's use this. So if H is a SILO3 subgroup, then 25 is basically this index, right? So from this, order of this quotient is 25, and this is equals to order of G by order of NH. This is 25. So order of NH is just order of G by 25, and order of G is 375. So order of NH is 15. So this implies NH is a subgroup of G of order 15. So in this case also we have a subgroup of order 15. Is it okay?
Yes.
So if you have any doubt in any step, you can ask. Okay, now let's do some problems on class equation as I have promised in the last season. So this is problem number 9. So first I will start with a basic application of class equation, then I will move on to some concrete problems on class equations. Okay, so let G be a group of even order. Okay, means G's order of G is of the form 2n for some n. Then, so that the number of elements of G of order 2 is odd. So given is G is a group of even order, we need to prove it has odd number of elements of order 2. So first of all, elements of order 2 exist in a group of even order, and the number of element of order 2 is always odd. So this problem can be solved by an elementary argument, but I want to do it using group actions to show that group actions can be used in a several ways. Actually, it is a very powerful tool. So let's try to understand why. Uh, so in the examples of group actions, I have given one example which in which, let's say, G prime is the multiplicative group of two roots of unity. Then we have saw G prime acts on G by 1 times G is G and minus 1 times G as G inverse, right? So this is a group action we have already saw. Now let's try to find the orbit decomposition or class equation of the group action. Then by the orbit decomposition of G prime, we have cardinality of the of G, sorry. So cardinality of the set is equals to sum of the cardinality of the distinct orbits, right? Where O1 up to OK are distinct orbits of the action of G prime on G. Now, if you remember, I have also found the orbits of this group action. So for G belongs to G, how the orbit looks like? It is just singleton G if G square is equals to E, and it is G comma G inverse if G square is not equals to E. So just you can check it by the definition, or you can go back to the earlier videos and you can see. So each orbit has cardinality either 1 or 2. So which orbits has cardinality 1? Which has for those elements whose square is the identity. Okay, so let S prime be the set of all those elements G whose square is identity. So for this type of elements, the orbit is singleton. So then the orbit decomposition gives it is cardinality of S prime plus cardinality of those orbits where this orbits has cardinality exactly 2. So we are just collecting those elements whose orbit is singleton set. So J is equals to 1 to up to R. Now order of G is 2n, right? So G here it is divisible by 2. Also this part is also divisible by 2. So that means 2 divides. So I am saying so order of S prime is basically order of G minus order of orbit of I1 plus dot dot order of orbit of IR. Now 2 divides G, order of G, and 2 divides this part. So 2 divides this whole number. So that means 2 divides order of S prime. So this implies order of S prime is even. Now S prime is this set. G belongs to G such that G square equals to identity. So E square is equals to identity, right? That means E belongs to S prime. So now E belongs to S prime. So what is this cardinality? S prime minus identity element. This cardinality should be odd because we are just excluding one element. So what is this set? This set is basically G belongs to G such that G square equals to E and G is not equals to identity. So this is the set of all elements of order 2, right? And cardinality of this set is odd. So we are done. So is it okay?
Okay, sir.
Yeah. So every group of even order has an element of order 2 and the number of elements of order 2 is odd. So this can be done by an elementary argument without using group action, but it can be done by using group action also. Okay, so we have saw product groups, Silos theorems. Okay, we need to see about P groups. So I will rest of the part will be on P groups and class equation. So let me define P groups properly first. Then I will come to the class equation of those things. So P groups. So a group G, okay, P has to be a prime number. Let P be a prime number. Then a group G is called a P group if every element of G is of order, every element of G has order some power of P, some non-negative integer power of p. So that means g equals to okay, how to write it? So that means if g belongs to g, then order of g is equals to p power e. Let's say eg. Okay, not e. Let's say p power n g for some ng greater equals to 0. So it depends on g, but it has to be power of p. So those types of groups are called p groups. So it can be an infinite group in which every element has power of p. But finite p group has special form. So a finite group G is a p group if and only if order of G is p power n for some n greater equals to 0. So there are infinite p groups according to this definition, but finite p groups is always of this form. Means order of G has to be some prime power. So these types of groups are special finite groups. I hope you have seen the definition in the lectures, but let's not worry about that. So just like a group of order 4. Okay, let's see one example. So Z mod 4Z, it is a 2 group of order 4, or Z mod 2Z cross Z mod 2Z. It is also a 2 group of order 4, but this one is cyclic and this one is non-cyclic. So this group is special group. This is Klein's 4 group. So is known as Klein's 4 group. Okay, now let's come to the class equations. Okay, so let P be a prime number and suppose G is a group of order PQ. Then find all possible class equations of G. So we have to find all possible class equations of a group of order PQ. So first of all, recall what is class equation. So one way to see that class equation is basically the orbit decomposition when G acts on itself by conjugation. So basically it is of this form. Okay, when G acts on G by conjugation. But when G acts on itself by conjugation, the orbits are basically conjugacy classes. So this is known as the class equation of G. So what is conjugacy class? So let me recall you. So conjugacy class of an element G is the set of all conjugates of G. And in this action, what are the stabilizers? So it is orbit of G here. And stabilizer of G here is same as the centralizer of G. So it is basically A belongs to G such that AG equals to GA. So this is the conjugacy class and this is the centralizer. So we need to found all distinct conjugacy classes and need to find this equation. And one more important thing to recall is the orbit stabilizer theorem. So it basically says order of G same as order of the orbit of G times cardinality of the stabilizer of G. So it is in terms of this group action, conjugacy class of G, order of the conjugacy class of G times order of the centralizer of G. Okay, I hope you can recall these things. Now let's come back to our problem. So G is a group of order PQ. So now order of G is PQ. So let G belongs to G. So we need to found this order of conjugacy classes of elements of G. So then two possibilities are there. Either G belongs to the center or it does not belongs to the center. Okay. Before that, let me do two cases. Case 1, G is abelian. So if G is abelian, then G is equals to ZG. Then for all G belongs to G, what is this orbit? Means what is the conjugacy class? So this is AG A inverse such that A belongs to G. But G is abelian. So these elements commutes. So this is exactly equals to G. So every conjugacy class is singleton. So in this case, the class equation is just 1 plus 1 plus 1 up to PQ times. Okay, so if G is abelian, then the class equation looks like this. So the so important thing is here. So G belongs to ZG if and only if the conjugacy class of G is singleton. So this is one small exercise you can try. It is very easy. So let's do the case 2 when G is non-abelian. Okay, so that means G is not equals to ZG. So what are the possible orders of ZG? Can you find it?
One.
Only one, or there are other possibilities? So ZG is a subgroup of G. So by Lagrange's theorem, order of ZG should divide order of G, which is PQ. So it can be 1, P, P square, or PQ, right? But since G not equals to ZG, it cannot be PQ. One possibility cannot be there. So this is by Lagrange's theorem. Okay. Also recall one thing. If order of G is P power n, then the center of G is non-trivial. So this thing has been proved in the lectures. So that means order of ZG is strictly greater than 1. So I think you can recall this thing. So we have only two possibilities. Now can you be more specific? Is it P or it is P square?
P square.
So you are saying order of ZG is P square. So actually it has to be of order P. So you use the G mod Z theorem. So if order of ZG is P square, then order of G mod ZG is PQ by P square, which is P. So this is a prime number. So this means G mod ZG is cyclic. So this means G is abelian. So which is a contradiction. So this is by G mod Z theorem. So this is a contradiction. So order of ZG has to be equals to P. Okay, I hope you have understood this. So
Yes.
first of all, order of ZG has to be greater than 1 because it's a P group. So we have only two possibilities, either P or P square. It cannot be P square by G mod Z theorem. Now let's come back to the class equation. So the class equation is PQ is equals to 1 plus 1 plus 1 up to P times because center has order P. So every element in the center has the conjugacy class singleton. So we have P singleton conjugacy classes and we have the other conjugacy classes. So let's say it is summation of conjugacy class of G where G does not belongs to ZG. And distinct conjugacy classes. Okay, so now if G does not belongs to ZG, so we need to found the order of conjugacy class of G. So what is the possibility of this? Can you guess? So we will be using this orbit stabilizer theorem. Order of G is same as order of the conjugacy class times order of the centralizer. Now then centralizer of G, okay, then ZG must be proper subset of centralizer of G and it must be a proper subset of G, right? Because every element in the center must commutes with G, so this subset holds, and centralizer is a subgroup of G. So this implies order of the centralizer is equals to P square, because ZG subset of CG implies order of ZG is strictly less than order of the centralizer. So that means order of the centralizer strictly greater than P, and centralizer of G, proper subset of G, implies this cardinality of the centralizer is strictly less than order of G. So this means order of CG is less than PQ. So what is the possibility? So order of the centralizer has to be order P square. So if centralizer has order P square, so what is the order of conjugacy class? So go back to the orbit stabilizer theorem. So order of the conjugacy class is order of G by order of the centralizer. So order of G by order of centralizer. So it is PQ by P square. It is P. So the summary is, if G does not belongs to ZG, is centralized conjugacy class has order P. So the class equation is PQ plus 1 plus 1 plus 1. This is P times plus some R times P, where R is the number of distinct conjugacy classes of order P. Okay, I hope up to this everything is fine. So we need to find R. Yeah, any doubt?
No.
Okay, so we need to find R. So this implies PQ minus P is equals to RP. So this implies R equals to PQ minus P divided by P, which is P square minus 1. So there are exactly P square minus 1 conjugacy classes of order P. So the class equation of G is PQ equals to 1 plus 1 plus 1. This is P times, and plus P plus P up to plus P. This is P square minus 1 times. Okay. So I hope you have understood this. Is it okay?
Okay.
Yes.
Yeah. So basically what we are doing. So if G is abelian, so every conjugacy class is singleton. So this is 1 plus 1 plus 1 up to PQ times. So this is for any finite abelian groups. So the main case is when G is non-abelian. So when G is non-abelian, we have first found the order of the center. Then we are distinguishing between the elements which are not in the center. So if G is not in the center, then its conjugacy class has P elements. So finally we need to find how many conjugacy classes of order P are there. So that is the summary. So we have done for groups of order PQ. Now let's do it for groups of order P to the power 4. So this is 12. So let G be a group of order P to the power 4 where P is a prime. And suppose order of ZG is exactly equals to P square. So we are specifying the order of the center in this case. Then find the class equation of G. So order of G is P to the power 4 and order of ZG is P square. So we need to found the class equation of G. So we will do it by the same method in the previous one. So if G belongs to ZG, then the conjugacy class is singleton. That we know. So the conjugacy class has order 1. So if G does not belongs to ZG, then what happens? Then ZG is a proper subset of the centralizer and it is a proper subset of the group. So that means order of ZG strictly less than order of the centralizer strictly less than order of G. This is P square. This is P to the power 4. So that means order of the centralizer has to be PQ. So again use the orbit stabilizer theorem. So order of the conjugacy class of G is order of G by order of the centralizer of G. So it is P to the power 4 by PQ, which is P. So every non-central element has P elements in its conjugacy class. So the class equation of G is p to the power 4 equals to 1 plus 1 plus 1. This is p squared times. So this is for elements in the center, and this is some r times p, where r is the number of distinct conjugacy classes of order p. So again we need to find this r. So this implies r equals to p to the power 4 minus p square by p. So this is pq minus p. Hence we have p to the power 4 equals to 1 plus 1 plus 1. This is p square times, and plus p plus p. This is pq minus p times. So this is the class equation of group of order p to the power 4 whose center has order p square. Is this clear?
Yes.
Okay. So let me quickly introduce the quaternion group. This will be the final one. So this is quaternion group. Okay. So let define G to be the set 1 minus 1, I minus I, J minus J, K minus K. Okay. Now we need to define a multiplication or operation. So where I square equals to J square equals to K square equals to minus 1, and how to multiply between I, J and K. So we'll multiply using this notation. So this is I, this is J, this is K. So if we go in this clockwise direction, we will get positive. Means if we multiply I with J, we will get K. If we multiply J with K, we will get I. If we multiply K with I, we will get J. And if we go counterclockwise, we will get negative. Means if we go I times K, means this direction, we will get minus of J. If we go K times J, we will get minus of I. And if we go J times I, we will get minus of K. So this is the rule of multiplication. So you can see that I times J is not same as J times I. So this is a non-abelian group. So let's so using this, okay, with respect to this multiplication, G is a non-abelian group of order 8. So we have 8 elements, so it has order 8, and it is a non-abelian group. So you can do the multiplication table by your own. So what is I square, j square, k square is -1. So that means I to the power 4, j to the power 4, k to the power 4 is 1. So order of -1 is 2, order of I, order of j, order of k, all are 4, and this is same as order of -I, this is same as order of -j, this is same as order of -k, and inverse of I is -I, because this is -I square, which is 1. Similarly for others. So you just do the multiplication table. So it has only one element of order 2, which is -1, and the rest 6 elements of order 4. So inverse of I is -I, inverse of j is -j, inverse of k is -k. So now what is the class equation of this group? So it is denoted by actually Q8. So what is the class equation of Q8? So one way to do is you just calculate the conjugacy classes manually by hand, because you know all the elements, so you can find the conjugacy classes of those elements and you can write. Or what we can do is we can observe that order of Q8 is 8, means its order is 2Q, and it is non-abelian. And we have done the class equation for group of order PQ. So let's go back to this. Yes, this one. So we have done it for both cases, for abelian and for non-abelian. So for non-abelian case, so this is the case 2. What is the class equation? So this is the class equation. So PQ is 1 plus 1 plus 1 P times, and P plus P plus P square minus 1 times. So just substitute these elements. So 2Q equals to 8 equals to 1 plus, here P is 2. So 1 plus 1 plus 2 plus 2 plus 2, because it is P square minus 1 equals to 3 times. So this is the class equation. Okay. So from this, one more thing you can say, we have only two ones here. So that means the center of Q8 has cardinality 2. And you can check that 1 and -1 is the center. So this group has so many interesting properties. You can do it by on your own. So I just wanted to introduce this group and the class equation of these groups. I hope this is okay. Okay, so do you have any doubt?
No, sir.
Yeah, okay. In the week 8 content, if you have any doubt, you can ask, or otherwise, we can end here. This is the last season, so I hope you have enjoyed learning with me. So, thank you for
Thank you,
joining.
sir. Thank you. Exactly.
Yeah, okay. So, if you have any doubt, you can mail me also, or you can put it in the discussion forum. So, thanks. We can end here.
Thank you, sir.
Yeah, okay. Bye.